A very good evening everyone. Welcome to the video on RF power amplifiers. So as the name suggests, the power amplifiers are devices that act as drivers to your circuits, which means without their presence the amplifier cannot work. Now coming to the design considerations, we talk of amplifiers for very high frequency, which means as we saw already in the previous videos, when we design RF networks, we cannot be using Z, H, Y and ABCD parameters. When we design RF devices, the type of parameters we use are called as the S parameters or the scattering parameters. So the first thing we need to know when we design an RF device is the knowledge about S parameters for that particular device. The second design consideration, if you see in this diagram, certain parameters are given, such as the frequency range, which is the bandwidth, the gain of the amplifier, and the power output. So a power output of 90 watt means this amplifier can be used for applications that require a 90 watt output. I cannot go and use this amplifier for a device or for an application that requires 180 watts to power up. So first we need to choose the load for which we are designing the amplifier, and based on the load we need to determine the parameters such as VSWR, gain, stability, etc. So there are two design parameters. The one is knowledge of the S parameters. The second one, we need to know what kind of load we are using, and based on the load these parameters has to be designed. Now coming to the characteristics of a RF power amplifier, we are going to see two important characteristics. The first one is the gain compression and the second one is the dynamic range. So let us start with gain compression. So gain is usually represented as a ratio of the output power, let me write it as P0, divided by the input power. So a plot of P0 versus Pi gives my gain plot. So here we have plotted the input power in the x-axis and output power in your y-axis. Now when you observe this graph, this is a linear scale. So this line which I am drawing is a linear line, which means the output increases in proportion to the input. If I increase the input by one value, the output correspondingly increases by a corresponding value. If I increase the input further, the output correspondingly increases by that corresponding value of input. Such a variation is said to be a linear variation. So the RF power amplifier behaves linearly up to a particular level of input power. If you observe at this point, after this particular value, the graph goes non-linear in range, which means it is not a straight line, it is linear, but at a particular point it deviates and becomes non-linear. One main parameter we need to know in this graph is called as the 1 dB compression point. The meaning of 1 dB compression point is we have the linear scale, we have the non-linear scale. Now when I add 1 dB to the non-linear scale, if I increase the non-linear scale by 1 dB, I can reach your given required linear region. So if in case I want to know the knowledge, if we want the knowledge of the linear region of the amplifier, but it actually behaves non-linearly, then if I add 1 dB to my non-linear characteristics, we can attain the linear region of the amplifier. Hope you're clear with what I'm saying. I'll just repeat it once again. This graph has two regions. Till a particular value it behaves linearly, which means as the input power increases, the output power also increases linearly. But after a particular value, there is a non-linear variation of the graph, which means there is no direct proportion. As the power increases, the output remains almost approximately near of the same values. So this is what we call to be a non-linear variation. But if in case I want to know the linear scale of my amplifier from the non-linear region, if I increase it by a value of 1 dB, this is my nonlinear region. If I increase this by a value of 1 dB, I can reach my linear region. And this point is what we call to be the 1 dB compression point. So the formula for 1 dB compression point of the output is given by, we are taking the nonlinear scale of the input to which I am adding 1 dB gain to get my required output power. So P out is given by a gain of 1 dB which is added to your nonlinear input scale. So this is the first characteristic, which is gain compression. So using the nonlinear scale, if I increase by a value of 1 dB, we can reach the linear region of your transistor. The second important characteristic of a RF power amplifier is the dynamic range. So dynamic range specifies the range in which our amplifier behaves in a linear manner. Now once again seeing this graph, from here it increases, it keeps on increasing till this point it is somewhat linear. After this it becomes non-linear. So from this range till this range, this is what we call to be the dynamic range of your amplifier. So the dynamic range specifies the region where the amplifier has a linear value of power gain. Right? And I'm not considering this from the origin. We consider this from a point called as P out MDS. So if we see here, the dynamic range is considered from this linear scale till P out MDS. MDS stands for minimum detectable signal. It is the smallest amplitude that can be detected by the RF power amplifier. Since RF covers very high frequency range, a very small value is difficult to detect in the RF ranges. So therefore we consider the minimum detectable range which the RF device can detect, and from there till a range where my amplifier behaves linearly, we consider that to be the dynamic range of the given amplifier. Now coming to the formula of the output power, it is given by these parameters. It is K, T, B, G0 and F. KT specifies the temperature variation. Now why should temperature be considered? If we see RF devices, they are mainly used for communication purposes. So communication means it is wired, wireless, where a lot of external environmental factors comes into force. So temperature is one main factor that affects the characteristic of any RF device. So this KT specifies the temperature variation of the given RF amplifier, and the nominal value of KT is minus 173.8 for 300 degree Kelvin. So KT specifies the temperature variation. B specifies the bandwidth which can be applied to the amplifier, or which the amplifier is capable of accepting and giving out the amplified output. G0 specifies gain of the amplifier. So about the gain we have already seen in our previous videos of transducer power gain. And S stands for noise figure. Noise figure is actually just a number. It specifies the amount of noise that is added to the given signal by our device. So our device here is the amplifier. So how much noise the amplifier itself adds to the given signal, that is specified by a term called as noise figure. So if the noise figure number is larger, it means the noise present is more. If the noise figure number is very small, we can say that the amplification will be much more efficient. So repeating the parameters, KT specifies the temperature variation, B specifies the bandwidth, which is the acceptable range of for the amplifier. G0 specifies gain of the RF power amplifier, and F specifies the noise figure that is contributed due to the amplifier itself. Now coming to the various types of distortions in the RF power amplifier. The first type of distortion is the harmonic distortion. So we already saw about harmonics in the previous topic of mixers. Harmonics are nothing but, for example, this is my required output frequency. Let this be 2 Hz. This is not the only output that is obtained. In addition to the required frequency, additional frequency bands which are multiples of the output frequencies are obtained. So if this is my required frequency, I don't obtain only this. I obtain additional frequency spectrums also. So this is what contributes to harmonics in your given circuit. So harmonic distortion is due to the fact that we don't get the fundamental frequency alone, but we get the multiples of fundamental frequency also, which contributes to power loss in your given system. The second type of distortion is your intermodulation distortion. So inter means in between two frequencies. So just look at the diagram at the back. This is your required amplifier. The amplifier is a two-port device. We have your input port here. We have an output port here. To the input port, I am giving two frequencies of values F1 and F2. And when you see at the output, the frequencies F1 and F2 are amplified. The magnitude has increased. But in addition to this, we have got two more additional components, which are 2F1 minus F2 and 2F2 minus F1. These additional components are because when we give two input frequencies which are of very close values, for example, if I give this to be 2 Hz, if I give this to be 2.1 Hz, when two frequencies are very close to each other, when I apply this to the amplifier gives the output such that the given frequency gets amplified, but in addition, distortions are introduced. So this distortion is what we obtain as the 2F1 minus F2 and 2F2 minus F1. Now intermodulation distortion is found by the difference of these two signals. This is your required signal, which is F2, and the multiple of F2 we have obtained is this one. It is 2F2 minus F1. So the difference between the F2 signal and the corresponding harmonic, this difference is what we call to be the intermodulation distortion of the amplifier. Now looking at the characteristic graph of the intermodulation distortion, we once again have the gain plot where we have plotted the input power versus the output power. Now we said that the intermodulation distortion, it is the difference between the original frequency F2 and the harmonic present, which is 2F2 minus F1. So we have plotted the original frequency. This is the plot of the original frequency, which is F2, and this is the plot of your harmonic, which is 2F2 minus F1. The difference between power levels of F2 and this harmonic is what we call to be the intermodulation distortion. This is actually a noise that is added in our circuit. And if you see in this original spectrum, the scale is 1:1. So 1:1 means it is output is to input. If I increase input by a value of 1, output proportionally increases by a value of 1. Increase input by a value of 2, output increases proportionally by a value of 2. That is why we call the scale to be 1:1, and this holds true for your original spectrum, original amplified signal F2. But this is not true with the noise spectrum which is present there. The scale here is 1:3. So 1:3 means if I increase the input power by a value of 1, the noise increases by a value of third, an addition of factor of 2. So we can say that the IMD increases to the square of the input power. The noise increases to the double, to the square of your given input power value. One more important parameter we need to know in the graph is called as the intercept point. So intercept point means I'm going to take the intersection of the two graphs, which is F2 and 2F2 minus F1. Now I'm going to draw the linear scale of both the graphs. So for F2, the original spectrum, this is the linear scale. It goes in a proportional way. Let it be the linear scale. Now for my noise signal 2F2 minus F1, this is my linear scale. Now these two will intersect at one particular point, and this point is what we call to be the intercept point of our given amplifier. The use of finding out this intercept point is, using this point, if we trace back down the graph, we can identify the regions of your original spectrum as well as your distorted spectrum. So on finding the intercepted point, we come back, we trace down the line to obtain what might be the original spectrum of the signal as well as what might be the distorted spectrum of our given signal. And the formula for intermodulation distortion, as said earlier, it is given by the difference between the original output, which is your F2, and the distorted output, which is 2F2 minus F1. So the difference in power levels of F2 and 2F2 minus F1, that gives our intermodulation distortion in the decibel scale. So to have a quick recap of what we saw in this video, we saw that S parameters are required to characterize RF power amplifiers. Also, only if we know what is the load I'm going to use. I need to know a knowledge of to which application I'm going to use this RF power amplifier, because only based on the application we can design the given RF power amplifier. So this was the first thing we saw. The second thing that we saw were the two characteristics of the RF power amplifier. The first one was gain compression and the second one was dynamic range. The third one what we saw was the various distortions that affect the efficiency of the RF power amplifier. So the two distortions were harmonic distortion and intermodulation distortion. So harmonic distortion is due to the presence of multiples of your fundamental frequency, which we saw like this. Like this is my required frequency. I don't get only this, I get additional frequency components also. So these are called as harmonics. The second one, intermodulation distortion. It is because when two input frequencies are given very close to each other, not only the two frequencies gets amplified, but in addition to them, we get extra frequency bands which contribute to intermodulation distortion. So I hope you're clear with this topic. If any doubts, you can refer our textbook, either Ludwig or Radmanish. Thank you.